Full explanation of flyback transformers and its application. A flyback transformer, also known as a line output transformer, LOPT, is a special type of transformer used primarily in switching power supplies and other high-voltage applications. It is unique because it stores energy in the air gap of its core and releases it when required. Here's a more detailed look at flyback transformers and their applications. Flyback transformers operate on the principle of storing energy in a magnetic field when the primary winding is energized, and then releasing that energy to the secondary winding when the primary current is interrupted. Here's a step-by-step explanation of how they work. Basic operation. Primary winding energized. When a switch, typically a transistor, connected to the primary winding is turned on, current flows through the primary winding. This current creates a magnetic field in the transformer core, storing energy in the core. The air gap in the core allows for a significant amount of energy to be stored. Energy storage. The magnetic field generated by the current in the primary winding stores energy. The voltage induced in the secondary winding during this time is of opposite polarity and typically not used in this part of the cycle. Diode in secondary winding is reverse biased. Primary current interrupted. When the switch is turned off, the current in the primary winding stops abruptly. The magnetic field collapses rapidly, inducing a high voltage in the secondary winding. Energy transfer to secondary. The induced voltage in the secondary winding is now of a polarity that forward biases the diode connected to the secondary winding. The stored energy in the magnetic field is transferred to the load through the secondary winding. The secondary winding delivers the energy to the load, resulting in the desired output voltage and current. Key components and their roles. Primary winding. The winding where energy is initially stored. Switch. Transistor controls the current flow through the primary winding. Core with air gap. Stores magnetic energy when the primary winding is energized. Secondary winding. Receives energy from the collapsing magnetic field and delivers it to the load. Diode. Ensures that energy flows in the correct direction from the secondary winding to the load. Load. The device or circuit that receives power from the secondary winding. Operating waveforms. Primary current waveform. When the switch is on, the current increases linearly due to the inductive nature of the primary winding. When the switch is off, the current drops to zero. Secondary voltage waveform. When the switch is on, the voltage induced in the secondary is negative or zero in ideal cases. When the switch is off, a high positive voltage is induced in the secondary winding. Advantages of flyback transformers. Simple design. Fewer components compared to other types of converters. Cost-effective. Often less expensive to manufacture. Isolation. Provides excellent electrical isolation between input and output. Disadvantages of flyback transformers. EMI. Electromagnetic interference can generate significant electromagnetic interference, which needs to be managed. Efficiency. Generally less efficient than some other types of transformers, like forward converters, especially at higher power levels. Flyback transformers are widely used in various applications due to their simplicity, cost-effectiveness, and ability to provide electrical isolation. They are particularly common in low to medium power applications. Energy storage in flyback transformers. The process of energy storage in a flyback transformer is a crucial aspect of its operation. Here's a detailed explanation of how energy storage works in a flyback transformer. Magnetic field and energy storage. Primary winding energized. When the switch, typically a transistor, connected to the primary winding is turned on, current begins to flow through the primary winding. This current creates a magnetic field around the primary winding, causing a buildup of energy in the transformer core. Role of the air gap. The core of a flyback transformer has a deliberate air gap, which increases the transformer's ability to store energy in the magnetic field. The air gap prevents the core from saturating quickly, allowing for more energy to be stored before the magnetic field reaches its maximum capacity. Energy storage formula. The energy stored, E, in the magnetic field is given by the formula equals 1, 2, 2, E equals 2, 1, L, P, I, P, 2, where L, P, is the inductance of the primary winding and I, P, is the current through the primary winding. As the current, I, P, increases, The energy stored in the magnetic field increases quadratically. Magnetic field buildup. As long as the switch is on and current continues to flow through the primary winding, the magnetic field and the stored energy continue to increase. The rate of increase in current and hence energy storage is linear because the voltage across the primary winding is constant. In an ideal scenario, energy release. Switch turned off. When the switch is turned off, the current through the primary winding stops abruptly. The sudden cessation of current causes the magnetic field in the core to collapse rapidly. Induced voltage in secondary winding. The collapsing magnetic field induces a high voltage in the secondary winding. This induced voltage is of opposite polarity to the voltage that was applied to the primary winding. The diode connected to the secondary winding becomes forward biased due to the induced voltage, allowing current to flow to the load. Transfer of stored energy. The energy stored in the magnetic field is transferred to the secondary winding and then to the load. The amount of energy transferred is the same as the energy that was stored in the primary winding's magnetic field. Example calculation. To illustrate, consider a flyback transformer with a primary inductance. Energy release. This 0.002 joules of energy is then transferred to the secondary winding and delivered to the load when the switch is turned off. Conclusion. The energy storage and release mechanism in a flyback transformer allows for efficient conversion and transfer of power in switching power supplies and other high-voltage applications. The air gap in the core plays a critical role in enhancing the energy storage capability of the transformer, making it suitable for various applications requiring efficient and isolated power conversion. Energy release in flyback transformers. The energy release process in a flyback transformer is as crucial as the energy storage phase. It involves transferring the stored energy from the transformer's magnetic field to the secondary winding and subsequently to the load. Here's a detailed explanation of how energy release works in a flyback transformer. Process of energy release. Switch turned off. When the switch, transistor, in the primary circuit is turned off, the current through the primary winding stops suddenly. This abrupt cessation of current causes the magnetic field in the core to collapse rapidly. Induced voltage in secondary winding. The collapsing magnetic field induces a high voltage in the secondary winding due to Faraday's law of induction. The induced voltage in the secondary winding is of opposite polarity to the voltage that was applied to the primary winding when the switch was on. Forward bias diode. The induced voltage in the secondary winding forward biases the diode connected to the secondary circuit. This allows current to flow through the diode and into the load connected to the secondary winding. Energy transfer. The energy stored in the magnetic field during the primary winding's energizing phase is now transferred to the secondary winding. This energy is delivered to the load as electrical power. The amount of energy transferred is equal to the energy that was stored in the primary winding's magnetic field. Current and voltage waveforms. Primary side. When the switch is on, the primary current increases linearly. When the switch is off, the primary current drops to zero almost instantaneously. Secondary side. When the switch is on, the secondary voltage is negligible or negative due to the reverse bias. When the switch is off, the secondary voltage spikes positively, causing current to flow through the load. Key components involved. Primary winding. Stores energy when the switch is on. Switch. Transistor controls the current flow in the primary winding. Core. Stores magnetic energy. Secondary winding. Receives energy from the collapsing magnetic field. Diode. Ensures current flows in the correct direction to the load. Load. Utilizes the transferred energy. Example calculation. Let's revisit the example where the primary inductance, L, P, is 1 mH and the peak primary current, I, P, is 2A. The energy stored, E, is 0.002 joules. Energy stored equals 1, 2, 2 equals 1, 2 times 0.001 H times 2 A. 2 equals 0.002 J. E equals 2, 1, L, P, I, P, 2 equals 2, 1 times 0.001 H times 2A. 2 equals 0.002 J. Induced voltage in secondary. Suppose the turns ratio of the transformer is 110 primary. If the primary voltage during the off phase was 100 V, the induced voltage in the secondary would be equals 100 V times 10 equals 1000 V. V S equals 100 V times 10 equals 1000 V. Energy transfer. The 0.002 joules of energy stored in the magnetic field is transferred to the secondary circuit. If the secondary load is resistive, the energy is dissipated as heat or used to power a device. Conclusion. The energy release mechanism in a flyback transformer involves the rapid collapse of the magnetic field, which induces a high voltage in the secondary winding, forward biasing the diode and allowing the stored energy to flow to the load. This efficient transfer of energy makes flyback transformers suitable for various applications, including power supplies and high-voltage generation. Design features of flyback transformers. Flyback transformers are designed with specific features to optimize their performance for energy storage, voltage conversion, and electrical isolation. Here are the key design features of flyback transformers. 1. Air gap in the core. Purpose. The air gap is crucial in preventing core saturation and increasing the energy storage capacity of the transformer. Function. By introducing an air gap, the magnetic path is interrupted, which allows more energy to be stored in the magnetic field of the core without reaching saturation quickly. 2. Core material. High permeability. Core materials with high magnetic permeability are used to efficiently store and transfer energy. Common materials. Ferrite cores are commonly used due to their high magnetic permeability and low losses at high frequencies. 3. Winding configuration. Primary and secondary windings. The primary winding is connected to the input power source, and the secondary winding is connected to the load. Turns ratio. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines the voltage conversion ratio. Isolation. Windings are often separated and insulated to provide electrical isolation between the input and output. 4. Switching element. Transistor. A transistor, such as a MOSFET, is used to control the current flow through the primary winding. Switching frequency. The switching frequency affects the size of the transformer and the efficiency of energy transfer. Higher frequencies allow for smaller transformer sizes, but may increase switching losses. 5. Diode and snubber circuit. Diode. A fast recovery diode is used in the secondary circuit to ensure current flows in the correct direction when the primary switch is turned off. Snubber circuit. A snubber circuit, comprising a resistor and capacitor, is often used to protect the switching transistor from voltage spikes caused by the transformer's inductive load. 6. Thermal management. Heat sinks, used to dissipate heat generated by the switching transistor and other components to prevent overheating. Ventilation. Adequate ventilation or cooling mechanisms are necessary to maintain optimal operating temperatures. 7. Shielding and EMI management. Electromagnetic shielding. Shielding is employed to reduce electromagnetic interference, EMI, generated by the high-frequency switching operation. Filtering. EMI filters are used to minimize noise and interference in the input and output circuits. 8. Control circuitry. PWM controller. Pulse width modulation, PWM. Controllers regulate the switching frequency and duty cycle of the transistor, controlling the output voltage and current. Feedback loop. A feedback loop monitors the output voltage and adjusts the PWM signal to maintain a stable output. 9. Safety features. Isolation. Electrical isolation between primary and secondary circuits ensures user safety and protects sensitive electronic components. Overcurrent protection. Protection circuits are included to prevent damage due to excessive current. Overvoltage protection. Prevents the output voltage from exceeding safe levels, protecting the load and the transformer. Application-specific design considerations. Power rating. The design must accommodate the power requirements of the application, affecting the size and type of components used. Voltage and current ratings. Components are selected based on the required input and output voltage and current specifications. Environmental factors. Considerations for operating temperature, humidity, and potential exposure to harsh conditions can influence the choice of materials and protective measures. Conclusion. Flyback transformers are designed with specific features to enhance their performance, efficiency, and reliability in various applications. The air gap, core material, winding configuration, and other design elements are carefully selected and optimized to meet the requirements of the intended use, whether in power supplies, high-voltage generation, or other specialized applications. Flyback transformers are widely used in various applications due to their efficiency, cost-effectiveness, and ability to provide electrical isolation. Here are some of the primary applications of flyback transformers. 1. Switching power supplies. AC/DC power supplies. Flyback transformers are commonly used in low to medium power AC/DC power supplies. They efficiently convert AC input voltage to a stable DC output voltage. DC-DC converters. Used in DC-DC converters to step up or step down DC voltage levels, often in battery-operated devices and portable electronics. 2. CRT displays. Television sets. Flyback transformers are essential in generating the high voltages required for the cathode ray tube, CRT, in older television sets. Computer monitors. Similarly, they are used in CRT computer monitors to provide the necessary high voltage. 3. Photocopiers and laser printers. Charging the photoconductor drum. Flyback transformers provide high voltage to charge the photoconductor drum, a crucial step in the printing process. Corona wires. Used to generate the high voltage for the corona wires in photocopiers. 4. Power over Ethernet. PoE. PoE injectors and switches. Flyback transformers are used in PoE systems to provide isolated power to remote devices over Ethernet cables, ensuring safe and efficient power transfer. 5. LED drivers. Powering LED lighting systems. Flyback transformers are used to convert and regulate the voltage for LED drivers, providing stable and efficient power for LED lighting. 6. Electric vehicle chargers. Onboard chargers. In electric vehicles, EVs, flyback transformers are used in onboard chargers to convert AC mains voltage to the required DC voltage for charging the vehicle's battery. Charging stations. Used in EV charging stations to provide isolated and regulated DC power for charging. 7. Medical equipment. Defibrillators. Flyback transformers are used in defibrillators to generate the high voltage pulses needed to restore normal heart rhythm. Diagnostic equipment. Used in various diagnostic devices requiring high voltage and isolation, ensuring patient safety. 8. Telecommunication equipment. Isolated power supplies. Used to provide isolated power supplies in telecommunication systems, ensuring reliable and stable operation. 9. Battery chargers. Consumer electronics. Flyback transformers are widely used in battery chargers for consumer electronics, such as smartphones, tablets, and laptops. Industrial battery chargers. Also used in industrial battery charging systems where isolated and regulated power is required. 10. Home appliances. Microwave ovens. Flyback transformers are used in the power supply circuits of microwave ovens to provide the high voltage required for the magnetron. Induction cooktops. Used in the power supply circuits of induction cooktops for efficient energy transfer and regulation. 11. Renewable energy systems. Solar inverters. Used in solar power inverters to convert DC voltage from solar panels to AC voltage for grid-tied systems or to regulated DC voltage for off-grid systems. Wind turbines. Used in wind turbine power conversion systems for efficient voltage conversion and regulation. 12. Audio amplifiers. High-fidelity audio systems. Flyback transformers are used in the power supply circuits of high-fidelity audio systems to provide stable and isolated power. Conclusion. Flyback transformers are versatile components used in a wide range of applications across various industries. Their ability to efficiently convert and regulate voltage, provide electrical isolation, and handle high voltages makes them indispensable in modern electronic devices and systems. Advantages of flyback transformers. Flyback transformers offer several advantages that make them suitable for a variety of applications. Here are the key benefits. 1. Cost-effectiveness. Fewer components. Flyback transformers require fewer components compared to other types of converters, such as forward converters, making them more cost-effective to design and manufacture. Simpler design. The simplicity of the design reduces the complexity and cost of the power supply, especially in low to medium power applications. 2. Compact size. High-frequency operation. The ability to operate at high frequencies allows for smaller transformer sizes, making them ideal for compact electronic devices. Integrated designs. The integrated design of flyback transformers helps in reducing the overall size and weight of the power supply unit. 3. Efficiency. Energy storage. Efficient energy storage in the magnetic field and its transfer to the secondary winding helps in maintaining high efficiency, especially in low to medium power applications. Reduced energy loss. Properly designed flyback transformers can achieve high efficiency by minimizing energy losses during the switching and energy transfer phases. 4. Electrical isolation. Safety. Flyback transformers provide excellent electrical isolation between the input and output, which is crucial for safety in many applications. Protection. Isolation helps protect sensitive electronic components and users from high voltage and current surges. 5. Versatility. Wide range of applications. Flyback transformers are used in a broad range of applications, from consumer electronics and medical devices to industrial equipment and renewable energy systems. Variable output. They can easily provide multiple outputs with different voltage levels by adding additional secondary windings. 6. Regulation and control. Output regulation. Flyback transformers, combined with appropriate control circuitry, provide excellent output voltage and current regulation, ensuring stable operation of the connected load. Feedback mechanisms. They support various feedback mechanisms for precise control of the output voltage and current. 7. High voltage capability. High voltage generation. Flyback transformers are capable of generating high output voltages, making them suitable for applications like CRT displays, photocopiers, and laser printers. Isolation of high voltage. They ensure safe and isolated high voltage generation, which is essential for many specialized applications. 8. Reliability. Robust design. Flyback transformers are known for their robustness and reliability, especially in harsh operating environments. Longevity. The design of flyback transformers contributes to the longevity of the power supply systems they are part of. 9. Flexibility in design. Scalability. The design of flyback transformers can be easily scaled to meet different power and voltage requirements, from small portable devices to larger industrial systems. Customizable. Designers can customize the winding ratios, core materials, and other parameters to optimize performance for specific applications. 10. Protection features. Overload protection. Many flyback transformers include protection features to prevent damage from overload conditions. Thermal management. Effective thermal management mechanisms are often integrated to prevent overheating and ensure safe operation. Conclusion. The numerous advantages of flyback transformers, including cost-effectiveness, compact size, efficiency, electrical isolation, and versatility, make them a popular choice for a wide range of applications. Their ability to provide high voltage, reliable operation, and flexible design options further enhances their suitability for modern electronic devices and systems. Disadvantages of flyback transformers. While flyback transformers offer numerous advantages, they also have some limitations and drawbacks. Here are the key disadvantages. 1. Electromagnetic interference, EMI. High EMI. The switching operation of flyback transformers can generate significant electromagnetic interference, which can affect nearby electronic devices and circuits. EMI mitigation. Additional components, such as filters and shielding, are often required to mitigate EMI, adding to the complexity and cost of the design. 2. Limited power handling. Low to medium power. Flyback transformers are typically used for low to medium power applications. They are less efficient and less reliable at handling high power compared to other transformer types like forward or push-pull converters. Thermal management. High power operation can lead to significant heat generation, requiring robust thermal management solutions. 3. Efficiency. Switching losses. At higher power levels, switching losses can become significant, reducing overall efficiency. Core losses. Energy losses in the core material, especially at high frequencies, can also impact efficiency. 4. Complex control requirements. Complex regulation. Maintaining stable output voltage and current requires complex control circuitry, such as pulse width modulation, PWM, controllers, and feedback loops. Design complexity. The need for precise control and regulation can increase the design complexity and development time. 5. Output ripple. High ripple. Flyback converters can produce higher output voltage ripple compared to other topologies, which may require additional filtering to smooth out. Sensitive applications. High ripple can be problematic in sensitive applications where stable and clean power is crucial. 6. Core saturation. Core saturation risk. The core can saturate if the transformer is not properly designed, especially if the air gap is not optimized for the specific application. Design constraints. Preventing core saturation requires careful design and selection of core materials and dimensions. 7. Voltage stress on components. High voltage stress. Components, particularly the switching transistor and the diode, are subjected to high voltage stress during operation. Component selection. This necessitates the use of high voltage-rated components, which can be more expensive and may have limited availability. 8. Limited scalability. Power scaling. Scaling up the power rating of a flyback transformer for higher power applications can be challenging and may lead to inefficiencies. Alternative topologies. For higher power levels, other transformer topologies like forward, half-bridge, or full-bridge converters are often preferred. 9. Transient response. Slower transient response. Flyback converters may have a slower transient response compared to other topologies, making them less suitable for applications requiring rapid load changes. Load regulation. Achieving tight load regulation can be more difficult due to the slower transient response. 10. Noise and harmonics. Switching noise. The high-frequency switching can introduce noise and harmonics into the power supply, which may affect the performance of sensitive electronic equipment. Filtering requirements. Additional filtering may be required to reduce noise and harmonics, adding to the overall design complexity. Conclusion. Flyback transformers, despite their many advantages, also have several disadvantages that need to be carefully considered in the design and application process. These include issues with EMI, limited power handling, efficiency challenges, complex control requirements, output ripple, core saturation, voltage stress on components, limited scalability, slower transient response, and noise. Addressing these drawbacks often requires additional components, careful design, and thorough testing to ensure optimal performance and reliability in the intended application. Flyback transformers are critical components in many modern electronic devices and systems, providing reliable voltage conversion and isolation in a compact and efficient package.